Hello everyone and welcome to this lecture. In the last lecture, we saw one of the most beautiful theorem about symmetric matrix. This theorem tells that for a symmetric matrix of order n, we can always get n orthogonal eigenvectors. Okay, and there are many applications of it. In this lecture, we will be making use of this fact to find the largest eigenvalue and the smallest eigenvalue and some other result also. So let me begin this, and these the result that we will prove it will be used. We will be using this in our future lectures. Okay, so let us start and let me write the statement. Okay, so yeah, so theorem is this. Theorem, let M be any symmetric matrix, let M be a symmetric matrix, of order n cross n, okay, then and with eigenvalues, suppose let me order these eigenvalues now. Lambda 1, more clear here, lambda 1 greater or equal to lambda 2 greater or equal to lambda 3 and so on lambda n. So there will be n eigenvalues. Now I have sorted them. So lambda 1 is largest, lambda is the smallest. Okay, very good. Then lambda 1 is indeed equal to, let me first write, maximum over this ratio. You pick all possible x, keep this ratio, find this ratio, and whenever this ratio is maximum, okay, that value, that basically this value will give you the number, the largest eigenvalue. Okay, and here x is of course non-zero. Okay, and then this you can actually equivalently write that maximum over all possible, this is actually equal to this thing when you can take norm equal to 1. Norm of x is when this restriction is, these two are equivalent things. Okay, very good. So and next thing is similar to largest one, the smallest eigenvalue is actually this, minimum of x transpose Ax. Remember, these x are any vector in the space of Rn. Okay, so n dimensional, basically there are n coordinates in x. Okay, and minimum, or this is equivalently I can write minimum over x transpose Ax. Remember, norm is what? Norm is nothing but x. So norm, let me write norm of x is nothing but x transpose x. Very good. So let us try to prove it, and maybe we can prove one more result. Let me write that result. So I will prove all this together. The third result is, suppose if x transpose Ax equal to lambda 1 norm x, okay, then this implies then Ax is equal to lambda x, Ax is equal to lambda 1x. Basically then x is the eigenvector corresponding to the largest eigenvalue. Okay, so let us try to prove these three neat facts. Okay, so proof, and in this proof I will begin with the use of spectral theorem, the theorem which says that any symmetric matrix will have n orthogonal eigenvectors. Okay, or for simplicity n orthonormal eigenvectors. Okay, so what I can do, see, there are n, so matrix is n cross n, there are n orthogonal eigenvectors. That means any vector in which basically any vector which belongs to this space, which belongs to Rn, can be written as linear combination of eigenvectors of M or A. What I have used the vector x M. Okay, so let me, here I am using A, so let me write it as A matrix. Sorry about that. Okay, now, okay. So yeah, so A is any symmetric matrix. Okay. Yeah, so X you can write as a linear combination of V1 plus V2 dot alpha and Vn, where these vectors V1, V2 up to Vn are eigenvectors. Let me write eigenvectors corresponding to lambda 1, lambda 2 up to lambda n. Okay, very simple. So I can write any vector x as a linear combination of these vectors. Very simple. Now this. Okay, so let me, like earlier, so let this V be the matrix which consists of these vectors V1, V2, Vn. Okay, Vn, very good. And suppose alpha is this vector which consists of these coefficients alpha 1, alpha 2 and alpha n. Very good. So that means x I can write, so x I can write as what I can write, yeah, linear combination. So x is nothing but V times alpha. Alpha is a vector, okay. So what will be x transpose x, by the way? X transpose x will be, yeah, so basically I will take transpose of it, is alpha transpose V times alpha, and B consists of eigenvectors. I am deliberately taking the eigenvectors which have unit length, so this will be equal to identity because these guys are orthogonal to each other. Very good. So this will be equal to this. Very good. So this will be indeed giving alpha transpose alpha, okay, which is nothing but sum of these coefficients. Yeah, alpha is, let me write, I equal to 1 to L. Very simple. Okay, very good. Now next thing is, what will be x transpose ax? X transpose ax. X transpose x, if I write in the same way, so this will be okay, so V alpha transpose V transpose A is the same matrix, and then yeah, V alpha. Very good. Oh, and then again I can make use of a spectral theorem. So this quantity is nothing but, in the previous lecture we have said, nothing but a D matrix, with a diagonal matrix in which there are eigenvalues lambda 1, lambda 2 up to lambda n. Okay, alpha. Okay, and remember the largest one will be on the first entry, first diagonal, and the second one, because we are ordering these vectors V as this. So V1, V2, V1 is corresponding to lambda 1, V2 is corresponding to lambda 2, lambda 1 is largest. So on the top of this D, there will be lambda 1, then lambda 2, and then lambda. Okay, very good. Yeah. So what next? Yeah. So basically, yeah. Let me actually open it. So this will be nothing but lambda 1, lambda 2 up to lambda n. Rest will be zeros. Okay. And then lambda, this will be, if you do this will be nothing but, remember these are vectors, so this will be, if you do this calculator, okay, so yeah, so this guy will be multiply with this vector and then lambda I, so this will be lambda I square, like this, only the lambda i's will be coming outside, and this is again I equal to 1 to n. Okay, very simple observation. Now Now this quantity, so basically let me again write this, X transpose AX equal to I equal to 1 and then lambda I alpha I square. I have written it again, so deliberately I have written it again. Okay, so this please keep in mind. Now I can write the first thing. So this quantity X transpose AX, which is equal to, again I'm sorry about that, again I'm writing 1 to n lambda I alpha I square. Okay, now check that this quantity will be always less or equal to, this quantity lambda 1 times why is it so? It is so because lambda 1 is greater than or equal to all the other eigenvalues. Okay, so if you see that I have taken lambda 1 outside, okay, so this quantity will be always holding, basically this inequality. Okay, so and this quantity is nothing but, we have just established this quantity is nothing but X transpose X. Basically this is equal to lambda 1 transpose lambda 1 and mod X, or X transpose X, whatever you want to say. Okay, am I done? Okay, so this only tells that X transpose AX can take at most this value, right? At most lambda times this. For any X, X transpose AX is always less or equal to this. Can the equality hold? If equality hold, okay, then I can write lambda 1 is nothing but X transpose AX divided by this not, right? But is the inequality holding? Okay, in fact then is the equality holding? In fact, when you replace X by, basically I want to find, is there any X for which this equality hold? Okay, so this quantity can be at most this, right? That means lambda can be, I mean, if I tells that, so lambda is always greater or equal to this number, right? This number mod X is nothing but X transpose X, always. But is the equality happen? Yes, indeed. When if you take X equal to nothing but V1, indeed there exists a vector V1 for which this happens, right? So if you draw, I mean just write what will be X trans, if you replace it, V1 A V1 will be, what will be this? This will be nothing but V1 lambda 1 V1, right? And this is equal to V1, sorry lambda, because V1 we have taken as orthogonal, the unit is equal to 1. Okay, so this is indeed, even if it is not, so basically we are dividing by the norms, it is still safer to say. Okay, so basically this, so we have always, and we have indeed found a vector such that this equality is happening. So that means lambda is indeed equal to the maximum of X transpose AX divided by X transpose X, or if you are considering norm of X to be equal to 1, this is same as writing X equal to 1 and this is, yeah, X transpose AX. Very good, very simple fact. Okay, so now let us move to the next fact, and which actually is almost similar. The next fact is what? That if you see this equation, right, I can write X transpose the same thing, okay, X transpose AX, which is equal to summation over lambda I alpha I square. Okay, now this quantity will always be lambda I. Now this quantity will always be greater or equal to lambda n and then summation over lambda i's. Why it is so? Because of this. Because lambda n is the smallest eigenvalue. Okay, so it will be, so this part will be always lesser than x transpose ax, which indeed means this, which indeed I can write as, and x transpose is, so basically this is, and lambda n is nothing but this part is nothing but x transpose x, right, or norm x. Okay, so that means lambda n is always less or equal to this ratio for any x, so x transpose x. Again the same thing, is the equality hold? Is there a vector for which equality is happening? Yes, if you replace x by suppose vn, it will be equal. So that means lambda n is indeed equal to the minimum of x transpose ax divided by x transpose x, which is nothing but this. And this fact we will make lot of use of this fact. Okay, very good. So, and this is about symmetric matrix, and we will be dealing with sometime Laplacian matrix, sometime adjacency matrix. Both are symmetric matrix, so this fact is quite useful for us. Okay, so now the next part that we have to, in fact the last part that we have to prove is this, right? So suppose the third part is, suppose if x transpose ax equal to lambda 1 x transpose x or norm x, right? This implies that ax equal to lambda 1 x, which means that x is an eigenvector corresponding to lambda 1. Okay, so let us try to prove this. Yeah, and I think we have already established that x transpose ax is nothing but, so let me again see this. So this was nothing but this quantity, right? So summation over lambda i's, okay, alpha i's square I equal to 1 to n. This was the fact that I am again using. Okay, and what was the next fact also that I have just calculated above? Yeah, so this quantity is equal to this. Very good. X transpose, what is x transpose x? It's nothing but this. Okay, and x transpose x is nothing but summation over alpha I square. Very good. Okay, now there can be, so remember alpha, what I have done is lambda 1 greater or equal to lambda 2 and so on. So maybe up to k, suppose there are k eigenvalues which are equal to the largest one. Okay, so basically it may happen that lambda 1 equal to lambda 2 equal to up to lambda k, and then this follow. Okay, lambda k plus 2 up to lambda n. Okay, so I have to tell you, I have to prove that. So if lambda 1 has, we call it actually multiplicity, the number of times some eigenvalue is repeating. So for example, lambda 1 is repeating k times. Okay, so we call it multiplicity of the, in fact to be precise, algebraic multiplicity of that eigenvalue. Okay, so we have to prove that lambda 1 is an eigenvalue, lambda 1 is eigenvalue corresponding to a vector x. Okay, so we have to prove that x is the eigenvector. Okay. Okay, By the way, such things, when suppose eigenvalues are repeating, we call it multiplicity of that particular eigenvalue. For example, here the multiplicity of eigenvalues is suppose k of the largest eigenvalue, because lambda 1 is kind of repeating k times, okay, and to be precise we call it algebraic multiplicity, the number of times some eigenvalue is repeating, okay, and we have to prove that x is an eigenvector corresponding to lambda 1. Okay, so how can we prove this? Okay, so okay, so maybe these two guys will again help us. Okay, so if you expand this, so what is given to us? Given to us is this quantity is equal to this. Okay, so basically this. So let me write x transpose Ax. It is given to us that this is nothing but lambda times x transpose x, and x transpose x we already know that this is equal to this. So basically this, right? X sum, okay, I equal to 1 to n, and this is equal to this also, right? So basically equal to summation over I equal to 1 to n. So lambda I alpha I square. What next? What conclusion we can derive from here? The conclusion that we can derive from here, remember the first k eigenvalues are same. I mean, I have taken the general case, right? K could be equal to 1, k equal to 2, k equal to maybe n also. Okay, doesn't matter. But here up to k, all the eigenvalues are same. Basically the multiplicity is k, and this k plus 1 is strictly lesser than this. Basically all these eigenvalues are strictly lesser than this. That means what? That means what? And these alpha I square are positive terms, right? That means in order to satisfy this quantity, alpha k plus 1 equal to alpha k plus 2 equal to dot dot alpha n is nothing but 0. Otherwise this equality will not hold, due to the fact that lambda 1 up to lambda k is strictly greater than all these eigenvalues, and alpha i's are positive numbers. Alpha I squares are the positive number. Hence if you see carefully from where I started, I have written x as a linear combination of this. So x indeed in this case can be written as this: alpha 1 v1 alpha 2 v2 up to alpha k vk. No need to write further because all these guys are 0. Okay, now so basically and these are the eigenvectors corresponding to lambda 1, because lambda 1 has k multiplicity, right? Because lambda 1 equal to lambda 2 equal to, so we have, so lambda 1 equal to lambda 2 equal to, again I am writing for simplicity. Okay, now so this is basically I can write this as lambda 1. Okay, so what now? X can be written as this. Now this is a linear combination of eigenvectors corresponding to eigenvalue lambda 1, and the linear combination will also be an eigenvector, right? How? So you can actually prove that, but otherwise it is a very simple exercise. So we have to prove that Ax will indeed be equal to lambda and x. How? See, if you multiply with A here, so this will be A v1 a v2 up to a vn, right? So this is equal to, if you see that, let me write it here. So everywhere there will be lambda 1, right? So you can take out lambda 1 outside. This will be nothing but alpha 1 v1 up to alpha k vk, and this vector is nothing but x, because we have just written as x is equal to linear combination of this. Okay, so this proves that x is indeed an eigenvector corresponding to the largest eigenvalue. So thank you very much, and we will now see more and more beautiful stuff in next lecture. Thank you very much.